Hello class, here is part 2 of our metabolic pathways. We're now at the citric acid cycle. In our previous discussion, we finished with glycolysis and we generated a 3-carbon chain called pyruvate. Pyruvate will migrate to the mitochondrial matrix, where the enzymes that are seen here in the tricyclic acid cycle are found. Pyruvate cannot directly enter the Krebs cycle. It must first be prepared. It must first have a carbon removed. So we need to take this 3-carbon chain down to a 2-carbon chain. This is what I call the preparatory phase. During this preparatory phase, one of the carbons is removed and it's transferred released in the form of CO2. Along in this phase, we're also removing a hydrogen and electrons, and that means we're creating an NADH. At the end of this preparatory phase, we make acetyl-CoA, which is a 2-carbon molecule. This acetyl-CoA can now bind to a 4-carbon molecule called oxaloacetate, shown over here on the left. 4 carbons plus 2 will give us 6 carbons. And now we go from one step to the next through the TCA cycle. Do not memorize every step. Please understand that we eliminate some of the carbons off of the chain in the form of CO2. And we make more of our electron carriers. A new electron carrier shown down here, moving from succinic acid to fumaric acid, is FADH2. Remember, for every glucose molecule entering the Krebs cycle, we get 2 pyruvic acids. And that means we get 2 turns through the TCA cycle. Again, in your homework packet, you're asked to know, where is this occurring? What do you begin with, and what do you end with? This is occurring in the mitochondrial matrix. You begin with 2 pyruvic acids, and you finish with 8 NADH, if I include the preparatory phase. 4 for every turn for the pyruvic acid that's turning. And 2 FADH2, and shown down here we have a net gain of 2 ATP. Again, this is accounting for the 2 pyruvate that are coming into the cycle. After this, we're going to still stay in the mitochondrion, but we're going to move to a different place. We're going to move into the inner mitochondrial membrane. Here's where we're going to find the electron transport chain. In the electron transport chain, there are different enzymes, protein complexes that are involved in this entire process. Do not memorize all of those complexes. Please understand that it is here where we cash in our NADH and FADH2. For every NADH, we get 2.5 ATP, and for every FADH2, we get 1.5 ATP. You need to cash in these amounts of ATP for all of the NADH and FADH2 that were made in glycolysis and the Krebs cycle. On the next slide, I'm going to show you the overall tally of how many ATP were made. I'm sure when I give you this tally, you might say to yourself, that's not the value of ATP I remember when I took biology with a different teacher. Each cell type can have a different outcome, a different efficiency for the amount of ATP generated per mole of glucose. I am going to give you a middle range. So the truth is, depending on the cell type, For every NADH, you can get anywhere between 2 to 3 ATP. And for FADH2, you can get anywhere from 1 to 2 ATP. So you'll notice for us, for our class, we're going to pick the middle value. I'm going to say 2.5 ATP for every NADH and 1.5 ATP for every FADH2. However, there will be one exception that I point out on the next slide. So let's start to calculate how many ATP we actually generated. First, in glycolysis, shown up here, we had a net gain of 2 ATP. Then we moved into the Krebs cycle. And remember, in the Krebs cycle, we generated 2 ATP from the actual cycle itself, a net gain. And that's shown down here at the bottom of our tally. Then, what about the NADH and FADH2s that we've generated? Well, let's first handle the ones that we generated in the Krebs cycle. We generated, shown here, 8 NADH. 8 times 2.5 gives me 20 ATP. We generated 2 FADH2. 2 times 1.5 gives me 3 ATP. But what about the NADH that came from glycolysis? Well, that had to cross the mitochondrial membrane. And when it does that, it loses some of its stored energy, its potential energy. So it won't cash out for its maximum value. Instead, those 2 NADH will cash out for 1.5 ATP. And that gives us 3 ATP for the NADH produced from glycolysis. So 2 plus 3 plus 20 plus 3 plus 2, a net average value is 30. That will be the class value we use. I understand that in other classes, you might have calculated 36 ATP or 38 ATP. It's okay. Your professor was not wrong. I am not wrong. It depends on the cell type and the efficiency of that cell burning its fuel. Not every car, I'm sure you'll appreciate, burns its gas the most efficiently. We're always speaking about efficient burning cars or efficient cars. Our cells are very much the same. So I picked the middle value to give a better view of all the cell types in our body. So let's talk about another fuel that we can burn, lipids. Lipids come in different varieties. They can be fatty acids, eicosanoids, glycerides, steroids, phospholipids like in our cell membrane, glycolipids like what we learned for blood typing. Those would be phospholipids with the sugar that's attached to them. Our focus will be on glycerides and fatty acids and how we can use those as fuel. These fatty acids and glycerides are going to have very long hydrocarbon tails. That means more hydrogen and more electrons to burn off or break apart from the larger molecule. Remember, it's those hydrogen and electrons that we cash in at the electron transport chain to make ATP. So here's a picture of a glycerol backbone shown up here in the top left purple picture. To each glycerol, we can attach a fatty acid. If there's one that is attached, it's a monoglyceride. If we attach 2, it's a diglyceride. If we attach 3, it's a triglyceride. And we can use these things for energy sources, fuel, if you will, insulation, and protection. So here's another view of a fatty acid tail. We have talked about fatty acids from phospholipids being cleaved away. In particular, we learned about arachidonic acid being cleaved away from a phospholipid when we learned about thermoregulation. These fatty acid tails, as you can see in this picture, are long chains of hydrocarbons, hydrogen and carbon atoms. Every hydrogen you see, along with its electron, is something that we can break apart from this molecule. On the next few slides, we're going to talk about beta oxidation. Beta oxidation occurs in the mitochondrion, where we're going to burn it. So first of all, let me back up. First of all, we're going to cleave these fatty acids 2 carbons at a time. And then those 2 carbons are going to shuttle into the mitochondria, and we're basically shuttling them in as acetyl-CoA, which we saw in the preparatory phase of the Krebs cycle. So then those acetyl-CoA, those 2 carbon groups, are now starting to be burned in the Krebs cycle. So lipid catabolism, breaking down lipids. Lipolysis is when we take those triglycerides that I showed you on a previous slide and split off the fatty acids and the glycerol. So that's lipolysis. But then we want to take those fatty acids and break them down 2 carbons at a time. So break off 2 carbons from this long chain. That's called beta oxidation. This will occur or start in the cytoplasm, but the 2 carbon fragments are shuttled into the mitochondria as acetyl-CoA, and they will enter the TCA cycle or Krebs cycle. There's going to be a lot of ATP that will be generated, but just not quickly. It takes time for lipids to be mobilized. Our primary fuel source, to remind you, is glucose. It is easy to mobilize. It is water friendly. Lipids are not. That's the sad truth when we are working out, trying to lose weight, trying to reduce the amount of fat we have. You have to work out aerobically, that means with oxygen, for about 20 minutes plus in order to start mobilizing your fats to use them as fuel. But once you get to that point, they are a robust fuel, lots of hydrocarbons. So beta oxidation is a 4-step process. You do not need to memorize the 4-step process, and I'm not putting it on this screen. I just want you to know that in this 4-step process, we're going to remove 2 carbons at a time. So if you look at the top of the picture, we can see highlighted in blue the 2 carbons that will be removed in the first steps of beta oxidation. So as we go through these 4 steps of beta oxidation, what are we going to get? We're going to get a lot of NADH, a lot of FADH2. We're also going to be able to cache these in, of course, in the TCA cycle. Well, let me back that up. We'll still make more in the TCA cycle, I should say, but we're going to cache them in the electron transport chain. And in the TCA cycle, remember, one of the steps, we actually make ATP in that cycle. So students often say to me, well, how many ATP can we get from burning a fatty acid? Well, it depends on the size. Is it an 18 carbon fatty acid, or are we starting with a 16 carbon, or even a 20 carbon fatty acid chain? For a typical fatty acid chain of about 18 to 20 carbons, you can actually get about 144 ATP. That's a lot of ATP for a fatty acid. But again, it takes a while for our fats to be mobilized. It takes a while for the body to start using them as fuel. One thing I want to point out here is that the acetyl-CoA, when we burn the 2 carbons off of the fatty acid, we are now shuttling that into the Krebs cycle, shown down here at the bottom, into the TCA in the form of acetyl-CoA. I'll remind you from a previous slide that the first step of the TCA cycle is where we join the 2-carbon acetyl-CoA to a 4-carbon molecule called oxaloacetate. Oxaloacetate is carbohydrate derived, which means it's derived from sugar, glucose. If you are deprived of glucose, if you are not able to get enough glucose into your cells, then your cells will be deficient of oxaloacetate. You will not be able to burn any fuel efficiently all the way to completion without the Krebs cycle. How would you get to the electron transport chain? You wouldn't be able to. On a previous slide, I said all roads lead to the mitochondrion, meaning the Krebs cycle, and then ultimately the electron transport chain. If you burn fats, you generate acetyl-CoA that will then enter the TCA cycle. Glucose, same story. Even proteins, same story. If you do not have enough carbs in your diet, if you cannot get sugar into your cells, then you will become deficient in oxaloacetate. You will not be able to burn your other fuels to completion. As a result, the fuels will be diverted into alternative pathways, much like pyruvic acid, if it didn't get to the mitochondrion for oxidative burning, for aerobic respiration, I should say. I told you that it would be turned into lactate. Well, with alternative fuels like fats, if they cannot be burned completely through the Krebs cycle, they too will enter alternative pathways. They will generate other metabolites. And these metabolites have a generic name called ketone bodies. There are 3. There is beta-hydroxybutyrate, acetoacetic acid, and acetone. They are listed at the bottom left of this slide. 2 of those ketone bodies are considered to be fixed acids. That means they must come out in your urine. The other one is considered to be volatile. It can come out in your breath. Acetone comes out in the breath, and acetoacetic acid and beta-hydroxybutyrate are the fixed acids that must come out in your urine. Interestingly, at night, when you're sleeping, what aren't you doing? You aren't eating. And as you are sleeping for about 6 to 8 hours, you switch from burning glucose to burning fats. And towards the time when it's, when you're ready to wake up, you've been without glucose for most cells of your body. During your sleep, you dream. And the body saves the glucose for the brain because even when you're sleeping, your brain is very, very active. So you burn alternative fuels when you sleep, like fats. Arguably, maybe we should stay home from the gym and just sleep more. In fact, some studies show that people who have more hours of sleep at night actually are thinner people. They have less fat. It is a correlation, not a cause and effect. We can talk about that some more if you want. When you wake up in the morning from burning these fats all day long, or all night long, I should say, and you wake up for your day, you have stinky breath, don't you? You have morning breath. That's actually the acetone coming out of your breath. So when you wake up in the morning, I want you to walk up to your loved ones and breathe real heavily out on their face and say, "Do you smell my breath? I've been burning fats all night long." The stinkier your breath, the more acetone you've made, the more fats you've been burning in your sleep.